Okay, hello everybody. This is Brian again, and I'm going to talk through problem 10.2. Okay, so first off, we're going to once again determine the principal stresses of sigma. This time our sigma is an equation instead of just giving it straight up to us. So sigma is now equal to tau cosine theta times E1 E2 plus E2 E1 and tau sine theta times E1 E2 plus E3 E1. So expanding that out, you can see we get tau cosine theta, this times plus tau cosine theta, this, etc. And that eventually goes straight into a matrix here, where we have including all of our zero terms that aren't like listed out here. We have a oh man, my camera's shaking. Okay, we have a stress tensor that is this right here. 0 tau cosine theta, then tau sine theta, then tau cosine theta, 0, 0, then tau sine theta, 0, 0. And when I first saw this problem, I really wasn't sure how to resolve the trigonometry terms in there. But I found that just trusting the process, eventually you get it to a format that's rather simple. Okay, so first, to get our eigenvalues, we need to find the determinant of the first half of the equation 10.1. So our determinant is equal to, once you get it laid out here and you take this, multiply it by determinant of this, and then do this, and then, going down. We're not going to cover how to do the determinant, but it eventually equals negative lambda times lambda squared minus tau cosine theta times this stuff here plus tau sine theta times this stuff down here. And simplifying that, we can eventually start to solve for lambda again. So taking the steps I took from here to there and there to here, we find this trig identity, cosine squared theta plus sine squared theta is equal to 1. It's a very key point here because it makes our equation so much simpler. We get down to here, I take out a lambda. I guess I took it out in the previous step. I take out a lambda, that's going to eventually be an eigenvalue of 0 minus lambda squared plus tau squared, breaking this into its two constituent um, components. We get negative lambda times lambda plus tau times lambda minus tau. And solving for our eigenvalues, we get 0 tau and negative tau. I'm starting to suspect there is a specific order for eigenvalues. I think people are arranging them either least to greatest or greatest to least. Someone happens to watch this video and knows the reasoning for that, let me know. Or if it's just habit, or if there's a convention on purpose. Okay, so now that we have our eigenvalues, we can find our eigenvectors, which correspond to our principal directions, right? So we know we have negative tau, 0, and tau as principal stresses, aka eigenvalues. And from equation 10.1, we can find the specific vectors n1, n2, n3 that are our principal directions by substituting lambda into the matrix. So our first substitution, we're going to use negative tau. Actually, I think I messed it up again. Yeah, I sure did. The that's the positive tau, so that means this is a plus. Regardless, it comes out the same way because we have plus and minus tau in our eigenvalue set. But anyway, we get these three sets of equations. I like to use nx, ny, and nz to keep it simple, although that's not exactly the right way to do it. We find that tau cosine theta times nx is equal to tau times ny, so we just cancel out the taus, and we get sine theta nx is equal to nz. I mean, we get cosine theta nx is equal to ny, and then we also get from the other equation sine theta nx is equal to nz. We're going to let nx equal 1 again, and we get this non-unit eigenvector n1. I denoted it with a prime because I want to normalize it. So I go ahead and I normalize it right up here by finding magnitude n. and I divide every value by magnitude n to get my eigen vector n1, which is 1 over square root of 2, cosine theta over square root of 2, and sine theta over square root of 2. Next, we do the process again, but this time we set lambda equal to 0. Doing that, we get these equations down here. And for our eigen vector components, nx has to equal 0. Then we have cosine theta ny is equal to sine theta nz, and cosine theta ny is equal to negative sine theta nz. Oh, I just said the same thing twice, but forgive me, I'm not going to redo the video for that. I just cancel out the tau and I wrote it again. But anyway, and we also have, so since we have it like this, there's only one thing that each of these components could equal to make this a true statement. So ny has to equal negative sine theta, and nz has to equal cosine theta. So you plug those two values back in, you have an equivalent statement. But without that, you don't. So this is what these values have to equal. So then the magnitude of n in this case is 1, so I'm not going to go through the normalized step that I normally have. We find that our second eigenvector is 0, comma, negative sine theta, comma, cosine theta. And now we do the last one. For the final eigenvalue, this time, let's see, did I do it right? Is that the right tau? Sure is. Okay, cool. So this time we substitute in negative tau, and we get this resulting matrix, set it to 0. And then we can find our eigenvector components, ny, nz, and nx. This time we actually do have to set nx equal to 1. So nz has to equal sine theta, negative sine theta, and ny has to equal negative cosine theta. And we normalize it, and we get our final direction, which is which is 1 over square root of 2, negative cosine theta over square root of 2, and negative sine theta over square root of 2. And that is our final answer.